Good afternoon, good morning, good night, or good evening. जिथे जो greeting accept करे हो. And we are reading a book, page number 86, and today's topic is reality of real numbers. Setting aside the notion of computability, real numbers are called real because they seem to provide the magnitudes needed for the measurement of distance, angle, time, energy, temperature, or of numerous other geometrical and physical quantities. However, the relationship between the abstractly defined real numbers and physical quantities is not as clear cut as one might imagine. Real numbers refer to a mathematical idealization rather than to any actual physical objective quantity. The system of real numbers has the property, for example, that between any two of them, no matter how close, there lies a third. It is not at all clear that physical distances or times can be realistically be said to have this property. If we continue to divide up the physical distance between 2 points, we would eventually reach scales so small that the very concept of distance in the ordinary sense could cease to have meaning. It is anticipated that at the quantum gravity scale of 10 to the power of 20th of the size of a subatomic particle, this would indeed be the case. But to mirror the real numbers, we would have to go to scales indefinitely smaller than this, that is 10 raised to power 200th or 10 raised to power 2000th or 10 raised to power 10 raised to power 200th of the particular particle size. For example, it is not at all clear that such absurdly tiny scales have any physical meaning whatever. A similar remark would hold for correspondingly tiny intervals of time. The real number systems is chosen in physics for its mathematical utility, simplicity, and elegance, together with the fact that it accords over a very wide range with the physical concepts of distance and time. It is not chosen because it is known to agree with these physical concepts over all ranges. One might well anticipate that there is indeed no such accord at very tiny scales of distance or time. It is commonplace to use rulers for the measurement of simple distances, but such rulers will themselves take on a granular nature when we get down to the scale of its own atoms. This does not in itself prevent us from continuing to use real numbers in an accurate way, but a good deal more sophistication is needed for the measurement of yet smaller distances. We should at least be a little suspicious that there might eventually be a difficulty of fundamental principle for distances on the tiniest scale. As it turns out, nature is remarkably kind to us, and appears that the same real numbers that we have grown used to for the description of things at an everyday scale or larger retain their usefulness on scales much smaller than the atoms, certainly down to less than 1/100th of the classical diameter of a subatomic particle, say an electron or proton, and seemingly down to the quantum gravity scale, 20 orders of magnitude smaller than such a particle. This is quite extraordinary extrapolation from the experience. The familiar concept of real number distance seems to hold also up to the most distant quasar and beyond, giving an overall range of at least 10 raised to power 42 and perhaps 10 raised to power 60 or more. The appropriateness of the real number system is not often questioned. In fact, why is there so much confidence in these numbers for the accurate description of physics, when our initial experience of the relevance of such number lies in a comparatively limited range? This confidence, perhaps misplaced, must rest on the logical elegance consistency, and mathematical power of the real number system, together with a belief in the profound mathematical harmony of nature. Complex numbers. The real number system does not, as it turns out, have a monopoly with regard to mathematical power and elegance. There is still a certain awkwardness in that. For example, square roots can be taken only of positive numbers and not of negative ones. From the mathematical point of view, and leaving aside for the moment any question of direct connection with the physical world, it turns out to be extremely convenient to be able to extract square roots of negative as well as positive numbers. Let us simply postulate or invent a square root of the number minus or negative 1. We shall denote this by the symbol of I, so we have a I square is equal to negative 1. The quantity I cannot, of course, be a real number, since the product of a real number with itself is always positive. For this reason, the term imaginary has been conventionally applied to the numbers whose squares are negative. However, it is important to stress the fact that these imaginary numbers are no less than real than the real numbers that we have become accustomed to. As I have emphasized earlier, the relationship between such real numbers and physical reality is not as direct or compelling as it may at first seem to be, involving as it does a mathematical idealization of infinite refinement for which there is no clear a priori justification from the nature. Having a square root of negative 1, it is now no great effort to provide square roots for all the real numbers, for if a is positive real number, then the quantity I into square root of a is a square root of a negative real number, that is negative a. There is also one another square root, namely negative I into square root of a. What about I itself? Does this have a square root? It surely does, for it is easily checked that quantity I plus 1 plus I over square root of 2 and also a negative of this quantity squares to I. Does this number have a square root? Once again, the answer is yes. The square root of 1 plus 1 over square root of 2 by 2 plus I square root of 1 minus 1 over square root of 2 by 2, or its negative is indeed 1 plus I over square root of 2. Notice that in forming such quantities we have allowed ourselves to add together real and imaginary numbers, as well as to multiply our numbers by arbitrary real numbers. The resulting objects are what are referred to as complex numbers. A complex number is a number in the form of a plus ib, where a and b are real numbers called the real part and imaginary part respectively of the complex number. Reading that back, high school coming into the picture. The rules for adding and multiplying two such numbers follow the ordinary rules of school algebra, with the added rule that I square is equal to negative 1, and there is a formula for it. A plus ib plus c plus id is equal to a plus c plus I in a bracket b plus d. Similarly, for a multiplication, a plus ib into c plus id is equal to ac minus bd plus I outside plus in a bracket ad plus bc. A remarkable thing now happens. Our motivation for this system of numbers had been provided to possibility that square roots can always be taken. It achieves this task, though this is itself not yet obvious, but it also does a great deal more. Cube roots, fifth roots, ninth roots, 10th roots, I plus 1th roots, etc. can all be taken with impunity, as a great 18th century mathematician Leonhard Euler was able to show. As another example of magic of complex numbers, let us examine the somewhat complicated looking formula of trigonometry that one has to learn in school. The sines and cosines of a sum of two angles, sine of a plus b is equal to sine a cos b plus cos a sine b, cos of a plus b is equal to cos of a cos of b minus sine a sine b, are simply the imaginary and real parts respectively, of much simpler complex equation, that is e of power to a plus b is equal to ea into eb. The quantity e is equal to 2.7182818285, the base of natural logarithms, and a rational number of mathematical importance comparable that of pi. Here all we need to know is Euler's formula, apparently also obtained many years by Euler by a remarkable 16th century English mathematician. Roger quotes that e of I into a is equal to cosine of a plus I sine of a, which we substitute into the equation above. Then we get cos of a plus b plus I of sine a plus b is equal to cosine of a plus I sine a into cosine of b plus I sine of b, and multiplying out the right hand side we obtain the required trigonometric relation, which is more any algebraic equations, that is a0 plus a1z plus a2z square plus a3z cube plus until an of zn is equal to 0, for which a0, a1, a2, an are complex numbers with an not is equal to 0, can always be solved for some complex number z. For example, there is a complex number z satisfying the relation z power to the 102 plus 999 z power to the 33 minus pi z square is equal to negative 417 plus I. Though this is by no means obvious, the general fact is sometimes referred to as the fundamental theorem of algebra. Various 18th century mathematicians have struggled to prove this result. Even Euler had not found a satisfactory general argument. Then in 1831, the great mathematician and scientist Carl Friedrich Gauss gave a startlingly original line of argument and provided the first general proof. A key ingredient of this proof was to represent the complex numbers geometrically and then to use a topological argument. The word topological refers to the kind of geometry sometimes referred to as rubber sheet geometry, in which actual distances are of no consequence and only the continuity properties of objects have relevance. Actually, Gauss was not really the first to use the geometrical description of complex numbers. Wallis had done this crudely about 200 years earlier, though he had not used it to nearly such powerful effect as had Gauss. The name normally attached to this geometrical representation of complex number is that of the Frenchman Jean-Robert Argand, who described it in 1806, although the Norwegian surveyor Caspar Wessel had in fact given a very complete description 9 years earlier. In accordance with this conventional but not altogether historically accurate terminology, I shall refer to the standard geometrical representation of complex numbers as the Argand plane. The Argand plane is an ordinary Euclidean plane with standard Cartesian coordinates x and y, where x marks of horizontal distance positive to the right and negative to the left, and where y marks of vertical distance positive upwards and negative downwards. The complex number z is equal to x plus iy is then represented by a point of Argand plane whose coordinates are x and y. So there is a plane in which they have imagined a y-axis as an imaginary axis, and they have a point. Note that the 0 is represented by the origin of the coordinates and 1 is represented as a particular point on the x-axis. The Argand plane simply provides us with a way of organizing our family of complex numbers into a geometrical, useful picture. This kind of a thing is not really something new to us. We are already familiar with the way that real numbers can be organized into the geometrical picture, namely the picture of a straight line that extends indefinitely in both directions. One particular point of the line is labeled 0 and another is labeled 1. The point 2 is placed so that its displacement from 1 is the same as the displacement of 1 from 0. The point half is the midpoint of 0 and 1. The point negative 1 is situated so that the 0 lies midway between it and 1, etc. etc. The set of real numbers displayed in this way is referred to as the real line. For complex numbers, we have in fact two real numbers to use as coordinates, namely a and b. For the complex numbers a plus ib, these two numbers gives us coordinate for points on a plane. The Argand plane, as an example, I have indicated in the figure approximately where the complex numbers u is equal to 1 plus I 1.3, v is equal to negative 2 plus I, w is equal to negative 1.5 minus I 0.4 should be placed. Okay, so they have pointed out those points in an Argand plane. It's pretty straightforward. The basic algebraic operations of addition and multiplication of complex numbers now find a clear geometrical form. Let us consider addition first. Suppose u and v are two complex numbers represented on the Argand plane in accordance with the above scheme. Then their sum u plus v is represented as the vector sum of 2 points, that is to say point u plus v occurs at a place which completes the parallelogram formed by uv and the origin 0. That is the construction actually gives us the sum. It's not very hard to see, but I omit the argument later. So they summed up a u and v complex number on an Argand plane and it makes a parallelogram. And that's a parallelogram law. The product uv also has a clear geometrical interpretation, which is perhaps a little harder to see. The angle subtended at the origin between 1 and uv is the sum of the angles between 1 and u and between 1 and v, and distance of uv from the origin is the product of the distance from the origin of u and v. This is equivalent to say that the triangle formed by 0, v and uv is similar to the triangle formed by 0, 1 and u. So they have a picture of the geometrical representation of a product, which says the product uv of two complex numbers u and v is such that the triangle formed by 0, v and uv is similar to that formed by 0, 1 and u. Equivalent, the distance of uv from the 0 is the product of the distance of u and v from 0, and the angle that uv makes with the real horizontal axis is the sum of the angles that u and v makes with this axis. The energetic reader who is not familiar with these constructions may care to verify that they follow directly from the algebraic rules for adding and multiplying complex numbers that were given earlier together with the above trigonometric identities. Construction of a Mandelbrot set, that's the next topic. We are now in a position to see how Mandelbrot set is defined. Let Z be the some arbitrarily chosen complex number. Whatever this complex number is, it will be represented as some point on Argand plane. Now consider the mapping whereby Z is replaced by a new complex number given by Z is equal to Z square plus C, where C is another fixed complex number. The number Z square plus C will be represented by some new point on the Argand plane. For example, if C happened to be given as the number 1.63 minus I 4.2, then Z would be mapped according to Z is equal to Z square plus 1.63 minus I 4.2, so that in particular 3 would be replaced by 3 square plus 1.63 minus I 4.2 is equal to 9 plus 1.63 minus I 4.2, that becomes 10 plus 63, 10.63 minus I 4.2, and 2 minus 2.7 plus I 0.3 would be replaced by, they're doing some mathematics over there. When such numbers get complicated and calculations are best carried out by an electronic computer. Now whatever C may be, the particular number 0 is replaced under this scheme by the actual given number C. What about C itself? This must be replaced by the number C square plus C. Suppose we continue this process and apply the replacement of the number C square plus C, then we obtain C square plus C of whole square plus C is equal to C raised to the power 4 plus 2C cube plus C square plus C. Let us iterate the replacement again, applying it to next to the above number to obtain, we go C of 4 plus 2C cube plus C square plus C the whole square plus C, that becomes C raised to the power 8, 4C raised to power 7, 4C raised to 6C raised to power 6, 6C raised to power 5, 5, 6C raised to power 4 plus 2C cube plus C square plus C, and then again to this number and so on. We obtain a sequence of complex numbers starting from 0. Now if we do this with certain choices of a given complex number C, the sequence of numbers that we get in this may never wanders from very far from the origin in the Argand plane. More precisely, the sequence remain bounded for such choices of C, which is to say every member of the sequence lies within some fixed circle center at the origin. A good example where the occurs the case C is equal to 0. Since in this case every member of the sequence is in fact 0, another example bounded behavior occurs when C is equal to negative 1, and for then the sequence is 0, negative 1, 0, negative 1, 0, I minus 1, minus I minus 1, minus I minus 1, I. However, for various other complex numbers C, the sequence wanders farther and farther from the origin to indefinite distance. That is, the sequence is unbounded and cannot be contained within any fixed circle. An example of this later behavior occurs when C is equal to 1, for then the sequence is 0, 1, 2, 5, 26, 677, 4, 5, 8, 3, 3, 0. This also happens when C is equal to negative 3. The sequence becomes 0, negative 3, 6, 33, 1086, and when C is equal to I minus 1, the sequence being 0, I minus 1, minus I minus 1, negative 1 plus 3I, negative 9 minus I5, 55 plus I91, negative 52, 57 plus I1011. The Mandelbrot set, that is to say, the black region of our word of the Torblatt name, is precisely that region of Argand plane consisting of point C for which the sequence remains bounded. The white region consists of those points C for which the sequence is unbounded. The detailed picture that we saw earlier were all drawn from the outputs of a computer. The computer would systematically run through possible choices of complex number C, where for each choice of C it would work out the sequence 0 C square plus C and decide according to some appropriate criterion whether its sequence is remaining bounded or not. If it is bounded, then the computer will arrange a black spot appear on the screen at the point corresponding to C. If it is unbounded, then the computer would arrange for a white spot. Eventually, for every pixel in the range under consideration, the decision would be made by the computer as to whether the point would be colored white or black. The complexity of Mandelbrot set is very remarkable, particularly in the view of the fact that the definition of this set is, as mathematical definitions go, a strikingly simple one. It is also the case that the general structure of this set is very sensitive to the precise algebraic form of mapping of map to z square plus c that we have chosen, many other iterated complex mappings, for example z is equal to z cube plus I z square plus c, will give extraordinary similar structures. There is indeed a kind of universal or absolute character to these Mandelbrot structures with regard to iterated complex maps. The study of such structures is a subject on its own within mathematics, which is referred to as complex dynamical systems. Next topic is Platonic reality of mathematical concepts. How real are the objects of the mathematician's world? From one point of view, it seems that there can be nothing real about them at all. Mathematical objects are just concepts. They are the mental idealizations that mathematicians make, often stimulated by the appearance and the seeming order of aspects of the world about us. But mental idealization, nevertheless, can they be other than mere arbitrary constructions of the human mind? At the same time, there often does appear to some profound reality about these mathematical concepts, going quite beyond and mental deliberations of any particular mathematician. It is though human thought is instead being guided towards some eternal external truth, a truth which has a reality of its own and which is revealed only partially to any one of us. The Mandelbrot set provides a striking example. Its wonderfully elaborate structure was not the invention of any one person, nor was it the design of a team of mathematicians. Benoit Mandelbrot himself, the Polish American mathematician and protagonist of fractal theory, who first studied the set, had no real prior conception of a fantastic elaboration inherent in it, although he knew that he was on the track of something very interesting. Indeed, when his first computer pictures began to emerge, he was under the impression that the fuzzy structures that he was seeing were the result of a computer malfunction. Only later did he become convinced that they were really there in set itself. Moreover, the complete details of the complication of the structure of Mandelbrot sets cannot really be fully comprehended by any of us, nor can it be fully revealed by any computer. It would seem that structure is not just part of our minds, but it has reality of its own. Whichever mathematician or computer buff chooses to examine the set, approximations to the same fundamental mathematical structure will be found. It makes no real difference which computer is used for performing calculations, apart from the fact that the differences in computer speed and storage and graphic display capabilities may lead to differences in the amount of fine detail that will be revealed and in the speed with which that detail is produced. The computer is being used in essentially the same way that the experimental physicists use a piece of experimental apparatus to explore the structure of the physical world. The Mandelbrot set is not an invention of the human mind, it was a discovery. Like Mount Everest, the Mandelbrot set is just there. Likewise, the very system of complex numbers has a profound and timeless reality which goes quite beyond the mental constructions of any particular mathematician. The beginnings of an appreciation of complex numbers came about the work of Girolamo Cardano. He was an Italian who lived from 1501 to 1576, a physician by trade, a gambler, and a caster of horoscopes. And he wrote an important and influential treatise on algebra Ars Magna in 1545, and thus he put forward the first complete expression for the solution in terms of surds, that is, ninth roots of a general cubic equation. He had noticed, however, that in a certain classes of cases, the ones referred to as irreducible, where the equation has a three real solutions, he was forced to take a certain stage and in his expression the square root of a negative number. Although this was puzzling to him, he realized that if he allowed himself to take such square roots, and only if, then he could express the full answer. Later in 1572, Raphael Bombelli, in a work entitled I Algebra or One Algebra, extended Cardano's work and began the study of actual algebra of complex numbers. While at first it may seem that the introduction of such square roots of negative numbers was just a device a mathematical invention designed to achieve a specific purpose, it later becomes clear that these objects are achieving far more than that for which they were originally designed. As I mentioned above, although the original purpose of introducing complex numbers was to enable square roots to be taken with impunity, by introducing such numbers, we find that we get as a bonus the potentially the potentiality for taking any other kind of root for or for solving any algebraic equation, whatever. Later find many other magical properties that these complex numbers possesses, properties that we had no inkling about at first. These properties are just there. They were not put there by Cardano, nor by Bomberly, nor Wallis, nor Codus, nor Euler, nor Wessel, nor Gauss, despite the all undoubted far-sightedness of these and other great mathematicians. Such magic was inherent in a very structural that they gradually uncovered. When Cardano introduced his complex numbers, he could have had no inkling of the many magical properties which were to follow, properties which go under various names such as Cauchy integral formula, the Riemann mapping theorem, the Levy extension property. These and many other remarkable facts are properties of very numbers with no additional modification whatever that Cardano had first encountered in about 1539. Is mathematics invention or a discovery? When mathematicians come upon their results, are they just producing elaborate mental constructions which have no actual reality but whose power and allegiance is sufficient simply to fool even their inventors into believing that these were mental constructions or real? Or are mathematicians really uncovering truths which are in fact already there, truths whose existence is quite independent of the mathematician's activities? I think that by now it must be quite clear to the reader that I am an adherent of the second rather than the first view, at least with regard to such structures as complex numbers and the Mandelbrot set. Yet the matter is perhaps not quite so straightforward as this. As I have said, there are things in mathematics for which the term discovery is indeed much more appropriate than invention, such as the examples just cited. These are the cases where much more comes out of the structure than is to put it to it in the first place. One may take the view that in such cases the mathematicians have stumbled upon works of God. However, there are other cases where the mathematical structure does not have such a compelling uniqueness, such as when in the midst of a proof of some result, the mathematicians find the need to introduce some contrived and far from unique construction in order to achieve some very specific end. In such cases, no more is likely to come out of the construction than was put into it in the first place, and the word invention seems more appropriate than discovery. These are indeed just works of man. On this view, the true mathematical discoveries would, in a general way, be regarded as greater achievements or aspirations than would be the mere inventions. Such categorizations are not entirely dissimilar from those that one might use in the arts or in engineering. Great works of arts are indeed closer to the God than are lesser ones. It is a feeling not uncommon amongst artists that in their greatest works they are revealing eternal truths which have some kind of prior ethereal existence, while their lesser works might be more arbitrary of the nature of mere mortal constructions. Likewise, an engineering innovation with a beautiful economy where a great deal is achieved in the scope of the application of some simple, unexpected idea might appropriately be described as a discovery rather than an invention. Having made these points, however, I cannot help feeling that with mathematics, the case for believing in some kind of ethereal, eternal existence, at least for more profound mathematical concept, is a good deal stronger than in those other cases. There is a compelling uniqueness and universality in such mathematical ideas which seems to be of quite a different order from that which one could expect in the arts or engineering. The view that mathematical concepts could exist in such a timeless, ethereal sense was put forward in ancient times by a great Greek philosopher Plato. Consequently, this view is frequently referred to as mathematical Platonism. I will have considerable importance for us later. In chapter 1, I discussed at some length a point of view of strong AI according to which mental phenomena are supposed to find their existence within the mathematical idea of an algorithm. In chapter 2, I stressed the point that the concept of an algorithm is indeed profound and God given notion. In this chapter, I have been arguing that such God given mathematical ideas should have some kind of timeless existence independent of our earthly selves. Does not this viewpoint lend some credence to the strong AI point of view by providing the possibility of an ethereal type of existence for mental phenomena? Just conceivably so, and I shall even be speculating later in the favor of view not altogether dissimilar from this, but if mental phenomena can indeed find a home of this general kind, I do not believe that it can be with the concept of an algorithm. What would be needed would be something very much more subtle. The fact that algorithmic things constitute very narrow and limited part of mathematics will be an important aspect of the discussions to follow. We shall begin to see something of the scope and certainly of non-algorithmic mathematics in the next chapter. So that was our chapter number 3. We are going through the book, and our next chapter is chapter 4, or my chapter, or I am reading, I am the reader. My next chapter is Truth, Proof and Insight. I will continue from here in the next video.